Today I'm going to talk to you about one specific paradigm I use in my work on sensory integration, and it is a nice way because I'm going to show you how what this paradigm measures, and then experiments we did to look at different deficits and different processes involved in sensory integration in different populations. So I am based in Queen's University Belfast at the School of Psychology, and my interests are primarily postural control, so how people keep their balance and how we stay standing on 2 feet, and it's quite a complicated process to do that, even though it looks very automatic and simple, and what happens when people start to have problems with balance. For example, older adults when they start to fall, or clinical populations with problems, like people with Parkinson's disease. So primarily I study healthy aging. So what happens when people are in their 70s and 80s if they don't really have any major health problems? How are they different from someone in their 20s and 30s in terms of their balance? I also study clinical groups, so people with Parkinson's disease and depression, and also atypical populations like people with neurodevelopmental disorders like autism. All these, the thing that all these populations have in common is that have some sort of deficit, some sort of difficulty in using sensory information to control their balance. So, but these deficits are not similar. They are quite different sometimes. The processes I study is a process called sensory reweighting. I will explain what that is, and also adaptation and learning. Sensory reweighting and adaptation go hand in hand. So I will show you what these are. So standing is difficult because we have 2 very small feet, and we have to stand, and we have a large body over these feet, and we have to keep always the center of gravity out of the base of over the base of support. So the Earth's gravitational pull is going that way, and we have to always keep the center of gravity out of the over the base of support. And this is what happens when it stays over, but when it goes out of the base of support, then there are serious problems. We can't do that for the first 12 to 15 months of our lives. So it's very hard to achieve that for babies. But gradually, we learn how to do this and how to walk. And during most of our life, it's not a problem. Balance is not a problem. You can just stand for hours without big problems. But gradually, as we get older, as we get in our 70s and 80s, this becomes a problem again. And becomes a problem also when we have certain pathologies. That's why older adults use walking sticks or any walking aids in order to keep their balance. So if you have a walking stick here, then suddenly your base of support increases, and that helps a lot with stability. What happens when we lose our stability? This is what happens. So this is an old person, and everything seems to be going fine, but he puts his foot in the wrong place, and suddenly the equilibrium is lost. The center of gravity is outside the base of support, and more importantly, he's not fast enough and he's not strong enough to put the foot back in the right place. And this is when things start to get difficult, because if he falls, he will have, it's possible that he will break his hip. That's how that's how broken hips happen. It's just you unavoidably fall on your side. And falls and hip replacements are very serious issues for health services in terms of cost, hospitalization. More than 1 in 3 people age 65 or older fall each year. After 60 years old, there's a very steep increase in falls. And falls are the #1 cause of fractures, hospital admissions for trauma, loss of independence, and injury deaths especially in older adults. Hip fractures. So surgeons are becoming really good at dealing with these hip fractures, but the problem is psychologically sometimes older adults are not very good in dealing with them. So if they stay in bed for too long, then they lose interest in physical activity, they lose their confidence of going out of the house, and it's a vicious circle then. And 25% of those who have fallen pass away each year falls are even harder for people, for example, with Parkinson's disease, who have additional pathologies, and they are more unstable and are more likely to fall. So balance is a very multidimensional problem. You have to deal with biomechanical constraints, strength, limits of stability, degrees of freedom, sensory strategies. So what do we do with information from the environment, and how do we get the information that something is about to happen? Orientation in space. How do we know about gravity, surfaces, vision, verticality, where is up, where is down? That's what the vestibular system does. The control of dynamics of gait and posture have to be controlled as well. There are certain movement strategies like reactive, anticipatory, and voluntary, which come into play when there is a perturbation. So somebody pushes you, somebody pulls the rug under your feet. And there are also cognitive processes, because older adults tend to think about their balance as they get older, because balance becomes less automatic as people get older. So these are the two main things I've studied so far: sensory strategies, so sensory integration and sensory reweighting, and cognitive processing. So how do we use cognition? Do we use thinking, basically, to support our balance? So today I'm going to talk to you about this part of my research. So in 3 parts, I'm going to talk to you about the mechanisms in general and how we think about these mechanisms, both physiologically and in terms of control. How we apply these principles to study healthy aging, and how do we apply them to study autism spectrum disorders and balance in these two groups. And finally, if we have time, I'm going to show you some work of ours on Parkinson's disease. So how do we start to study these things? So we know that there are 3 systems involved in balance. Information from the inner ear, which works like a gyroscope and tells us when the head is turning, but it only tells you about the head, doesn't tell you anything else about the body. You have to integrate this information to tell you about the body. So if my head is moving this way, this way, this way, the 3 rotations are picked up by 3 different gyroscope type systems called the semicircular canals, these 3, and also linear acceleration, so forward and backward and sideways. Vision tells me where fixed points are in space. So if I look there, and I know that if this is coming towards me, then I'm properly swaying. So that's how I interpret visual information. And information from proprioception is also important. This is information inside the muscles, coming from inside the muscles. So when a muscle is stretching or contracting, I get the information that if for example, if this muscle is stretching, then I know that I'm going forward. If this muscle is stretching, then I know that I'm going backwards. All this information has to be integrated to tell me where I am in space and whether I'm stable or not. This information from the 3 sources is weighted based on its relative reliability using a maximum likelihood estimation. So the more reliable one source is, the higher the weight. So if I'm standing here, then I use vision quite a bit. But if I close my eyes, then vision is out. So I have to upweight the other 2 sensory modalities. And this is basically the primary process I use. This is called sensory reweighting. What happens when you remove a modality? What happens when you add noise to one sensory modality of the 3? And how do the other 2 cope? How do they upweight and downweight to keep the body stable? So when standing in a stable, well-lit environment, vestibular is about 15%, visual is about 35%, and proprioceptive is about 50%. But it's never constant. It's always changing, and it's dynamically adapted. How do we think about this in terms of a model, and in terms of deriving hypotheses and doing manipulations? So you have visual information from the eyes, vestibular information from the inner ear, and proprioceptive information from the whole body, but primarily from the ankle joint. This comes through to the brain. This multisensory information comes to the brain, and the brain decides, is the body at a stable place or is it in an unstable place? So I'm standing now, my body doesn't have to do much. But if I'm starting to lean backwards, then this will be detected. And if it's detected, if a change is detected, then the brain sends a motor command to the muscles to correct this posture. And this happens constantly until it's a feedback loop. And it happens constantly until you get back to a stable place. So it's an error correction. What's it called? Yes, it's a feedback mechanism. So how do we test this system? So one way is to introduce inaccurate information in one of the systems, and because proprioception has the most weight, it's the highest weight, it's the one that is more likely to show something if you manipulate it. And we use a technique called sway referencing. So normally you have 3 weights, one for graviceptive, so one for vestibular, one for proprioceptive, and one for visual, and this equals to 1. If you introduce if you remove one of these, or if you introduce inaccurate proprioceptive or vestibular information, then this changes from 1 and you have to return it back to 1 using that mechanism. So there are 2 ways of inaccurate proprioceptive information. You can use sway reference or you can use reverse sway reference. So you can either introduce negative feedback or positive feedback. So this is how it works. So we have a participant on a surface, and normally you have your ankle angle, and let's say it's about 90 degrees. So you have no vision. When you sway a little bit forward, this angle changes. The muscle lengths change here. So they tell your body, correct 5 degrees. Corrects 5 degrees. Everything's fine. To play with the system and to fool it, what we do is we record. So basically, weight for graviception and weight for proprioception here is 1. So everything's fine. If you sway 5 degrees, what we do is then we record the ground reaction forces on this platform, and we tilt the platform with a motor, so that when you sway 5 degrees, this angle doesn't change. So proprioception now is telling you you're not swaying. So you only have the vestibular system to tell you that you're swaying. So what you have to do now is gradually reduce the weight of proprioception, increase the weight of vestibular to adapt to this manipulation. So basically what happens is proprioceptive information is ambiguous. You don't generate enough torque on the ankle joint to correct. You undercorrect, and then the body moves slowly in about 0.1 hertz, about 1 cycle every 10 seconds. So it goes very slowly forward and very slowly back, because it's not producing enough torque to correct. This is what that looks like. So, So this is body sway. So before you start sway referencing, it's very little. This is 5 degrees, and then it starts and it goes very slowly forward and back, and gradually gets smaller because it adapts. This adaptation means that proprioception is down-weighted and vestibular is up-weighted to, and that's how you adapt. And this is the time frequency the time frequency density of that. So you go from very slow movements to less of that, of these slow movements. But what you also see here, there's a little bit of an after effect. So when the platform stops, the body still moves more than this. So that's very interesting, and I'll show you a lot about that. In modeling terms, what happens is basically the same. So you have 60% proprioceptive, 40% vestibular, and what has to happen when sway referencing starts is proprioceptive has to be reduced and vestibular has to increase. And if that doesn't happen in a simulation with a robot, the robot falls over. If there is if there is reweighting, then there's a return to stability. But as you see, there is a delay here. So it takes a few seconds to implement this change in weights. And this delay may be different depending on if a population has a problem with this process. So it's a nice way to see, to compare different populations. So what we did was we compared young and older adults in this. So we said, we wanted to see how people cope with changes in sensory information that may lead to a fall. So we had 14 young adults and 13 healthy older adults. One older participant could not perform the task. It was too hard, so they were very unstable. So we excluded them. We chose them to have no major disorders and no fall accidents in the last 6 months. And they were very healthy in terms of, this is the mini mental state examination. So cognitively, they were very healthy. So instead of using a surfboard, we used this system. And this is the platform that tilts, basically. So they're standing here. They were wearing a harness. They were very safe. And they were standing here for a number of minutes. So what we did was we asked them to stand on a fixed surface for 3 minutes to establish a baseline with eyes closed. And then they started sway referencing for 3 minutes. They took a break, another 6 minutes, another break, another 6 minutes, and then 3 minutes moving, 3 minutes fixed, here to study the after effect. So we found very interesting things. There was a platform moving in the opposite direction, but I'm not going to go into detail on this because it shows very similar results. So when the platform is fixed with eyes closed, there is a small age difference. You see here the white dots are a little bit higher. So this is the path length, so how much the body sways in every 35 seconds. So this is divided in epochs of 35 seconds. So you see that young adults are moving less than older adults. And then when we started sway referencing, you see that that increases quite a bit. The age difference remains. However, both young and older adults are doing fine in adapting. So they reduce their sway over time. But their lines are relatively parallel. They're not, older adults are not doing any worse. If you ignore this initial difference, they don't really do any worse than young adults. So they're very good in adapting to this environment. Both groups are very good. But when we stop the platform, young adults return to baseline. So basically we measure how long does it take them to return to baseline. And this is the baseline for young, this is the baseline for old. Young adults take about 35 seconds to one point here to return to baseline. Older adults take about 3 minutes to return to baseline. So if they were really good at adapting, but they were really bad at de-adapting. So basically here they have to change the weights of the two channels, and here they have to change the channels back. So going back to normal was very hard for them. Why is it so hard? So we looked at the spectral components as well of that, just to see if that fits the model. So the model we use to predict this says that if you go from, in sway referencing, you would go from 0.1 hertz, which reflects undercorrection, to 1 hertz, which reflects overcorrection. And you switch from slow to fast. So if you see typical older adults, this is, sorry, go one back. Yeah, so this is the slow 1 hertz frequency. This is about, this is 70 seconds, so very slow frequency. And this is in the analysis of the frequency domain. Most of the power is at about 0.1, 0.2 hertz. And then slowly they return, and this is less, this is a bit less sway here, but again at about 0.1 hertz. But then when the platform stops, they go to a very fast pattern, which is about, then it flips from 0.1 hertz to 1 hertz. So this goes from undercorrection, so going very slowly because we didn't correct, to overcorrection, to go like this. And that lasts for most of the 3 minutes. But we don't know why. We don't know why they are fine when you introduce a very unstable environment, but when you remove it, they have serious problems with it. So our results show high instability, high demand for reduction in sway. Older adults have more sway and adaptation, a longer after effect. But their problem is disengaging from The problem is disengaging from a well-adapted pattern. So they can learn something, they can adapt to something, but when they have to de-adapt from it, they find it really hard. We see this also in studies of cognition. If you teach them a pattern, then unlearning it is very hard. They seem to like what they know, and they don't like to change, is perhaps another way of saying that. So that's one explanation, but it's not really theoretical. It doesn't really come directly from our... So we wanted to examine this further. So what we did then... Sorry, that's forward. Press here. We also wanted to see what's happening at the level of muscle activations. And we wanted also to match their sway between young and older adults. So I'll show you what we did here. So this is work by my former PhD student, Chesney Craig. We did 3 studies on this phenomenon. So we know that people co-contract during sway referencing. If you go on the platform, you feel that you're contracting your muscles, both agonist and antagonist. You're contracting your muscles a lot because it's impossible to predict how the platform is going to move. So older adults show more sway and greater co-contraction in general in these studies. But we don't know why they co-contract and whether that could explain our findings. So we did a shorter study. So we had 2 minutes of baseline, 3 minutes of sway reference, and 3 minutes of the after effect. We measure muscle activations from the medial gastrocnemius and the tibialis anterior, so the muscle that contracts when you go forward and when you go back. And we also tried to make young adults as bad as older adults during adaptation. So basically what we did is we made the sway referencing for young adults harder. So again, baseline, small differences here. In this case, they were not significant between young and older adults, standing with eyes closed. When we introduced sway referencing, we saw that the 2 groups didn't differ because we made young adults as bad as older adults. In fact, older adults were faster at some point here compared to young adults. But then more or less they were similar. However, still at the after effect, they showed 2 minutes of an after effect. Older adults did. Young adults, again, only 30 seconds. So even if you match here, the after effect is still there. So it doesn't make any difference. In terms of co-contraction, we see that for the same amount of sway, so here they were swaying for the same amount, the co-contraction was bigger in older adults, both in the beginning of adaptation and in the beginning of the after effect. Wherever there's a change in the environment, wherever there's a change in their pattern of sway, older adults, the first thing they do is they co-contract. They stiffen their ankles, or they stiffen any joint that might be perturbed to protect themselves. So it's a standard strategy, both here and here. So we learned a few things, still haven't. So the after effect persists even when sway is the same. Co-contraction is greater, and it follows the pattern of sway. But we still don't know about the after effect. Why are they so slow? You'd think that it's the same process as in adaptation backwards, but there's something more there. One idea is that when you introduce sway referencing, they are very unstable, so they have to do something about it. But when you remove sway referencing, they're stable, so they don't really have to do anything actively to protect themselves from a fall. And as I was thinking that, it occurred to me that we don't tell them anything. We don't tell them when the platform starts, and we don't tell them when the platform stops to make sure that whatever happens is automatic. It's natural. It doesn't really, they don't have to actively do anything. So one idea then we thought, could it be perceptual? Could it be that they don't know that the platform stops, and that's why they don't do anything? So in the next experiment, we did exactly the same thing. but we gave them a push button. And we said, when the platform stops here, press the button. So we tested 3 groups here. We tested a group of young, a group of old, and a group of old people who had fallen in the dance more than once. We saw that there were no differences in baseline. There were no differences in adaptation, even for the fallers. Fallers showed the most sway. Older adults were in the middle, and young adults were lower, as we expected. Fallers showed 1 minute of after effect. Older adults showed 2, maybe 3, 1.5 to 2 minutes of after effect. That was strange. So, when they pressed the button, young adults pressed at about 5 seconds. Older adults and fallers pressed at about 40 seconds. So for 40 seconds, they didn't know that the platform had stopped. They had to. So they had no idea. So at this point, and maybe the beginning of this one, no idea that the platform has stopped. So for them, they don't have to do anything. If you don't know that something has changed, then you don't have to do anything. Of course, there is the thing that Raimundo and I were talking is that it's the best way to access a perceptual process like this. It's probably not, but this is the only way we could do that. So from this, we can conclude that all adults don't know. They don't perceive that the platform stopped, and until they do, they don't really know, they don't really activate this process to reduce sway. So can they do it? Older adults are as fast as young adults in postural adaptation. They were very good. We have evidence from many other parts of the literature to say that older adults are very good in adapting and in learning. They haven't lost the ability to learn. They're much slower in the adapting. And what we found is this movement platform illusion. This is our latest work. It just came out. And basically the conclusion is that if you can't perceive a problem, it's very hard to fix it. If they don't know that the platform stopped, then they don't engage in the process of correcting their sway. So that's where we are now. So the next experiment, so in psychology, we tend to do one experiment after the other to eliminate factors or to try and see what happens. So in our next experiment, I tell them when the platform stops versus not telling them. And I'm thinking, if I tell them that when the platform stops, will this after effect go away? Because that's how we can prove that it's that knowledge that they're missing. So that's what we're doing now. So this was our work on healthy aging, on this phenomenon in general, on sensory reweighting. But sensory integration problems are not only seen in people with who are older. There are sensory integration problems also in people with autism. People with autism have problems processing sensory information from the environment. This is shown primarily in their social interaction and communication. We know that when they interact with other people, they have problems. But they also show problems in movement. And because they show problems in movement, it's likely that these problems come from problems with sensory information and perception. So, we also know that they have problems in balance. So 1 in 59 children by now are diagnosed with autism. The diagnosis is increasing dramatically. And recent research shows that they have processing abnormalities, hyper and hyporeactivity. So basically the way in which they perceive sensory information is different from people without autism, and they probably upweight or downweight sensory information compared with neurotypicals. So that's what they mean by hyporeactivity and hyperreactivity. So they show motor deficits, including balance. And there weren't many studies about the processes of balance. So most studies would look at standing with eyes open, standing with eyes closed, standing with on one leg and eyes closed, and that sort of thing. Very basic measures. So in the first study, we looked at autism with sway referencing. So we looked at standing on a fixed surface, standing on a surface with where the cabin is moving, the surround is moving, so manipulating visual information. When where the support is moving, so manipulating proprioceptive information, and both visual and proprioceptive. And we said 15 people, 15 adults with autism and 15 adults without autism. What we found was, as you make sensory integration demands bigger, the effect of autism increases, and it's probably multiplicative rather than additive. So the solid lines are the control group, and the dashed lines are the autism group. So especially in this condition, when sensory integration demands keep increasing, then this is where balance breaks down. So there's clearly a problem with sensory integration, but it's incomplete to say much more about that, because we don't know if it's because proprioception has a problem, because both have a problem, or if there's a problem of adaptation, as we've seen before. So we did a second study to look at adaptation, to look at sensory processing, focusing on proprioception in autism, to see whether we can show similar patterns that we saw in older adults, showing that there is a deficit. So what we did was we measured proprioception first to see if proprioceptive information that comes from the muscles, if that has a problem, and then we measured sensory integration using the paradigm that I showed you before. So sensory information, we measured it using a proprioceptive matching task. So you put your foot, the participant's foot on a fixed place, and then you ask them to match that position with the other foot. This is one way. This is called proprioceptive matching or joint position matching, and this is one way to measure proprioceptive acuity. The ankle joint, because that's the most relevant for balance. These differences were not significant. We can't say that there are significant differences between the two groups. This is neurotypical, and this is autism. Sorry about that. And then we did the same thing with the balance task. So in the balance task, this is the example of a neurotypical control. This is what you see here is the ankle angle, the angle between the floor and the ankles. And you see that there's very little sway here. When we introduce sway referencing, the sway goes up, but gradually it reduces. And then there's a little bit of an after effect. In people with autism, there is again this baseline, but when you introduce sway referencing, they don't seem to be reducing it. In fact, here you can see that there is an increase in sway. So there's definitely no adaptation. This is one participant, and this is the whole 480 seconds, so 8 minutes. So if we look at the means, we see a relatively similar picture in the control group. So in neurotypical controls, baseline, an increase when sway referencing is introduced, and then a gradual decrease and adaptation relatively quickly, and the after effect. In people with autism, we see the increase, which is not that much bigger from people without autism, but they don't adapt. There is a small adaptation, but then it gets worse again. So there's a very big age difference that doesn't exist at baseline, and doesn't exist at the after effect either. Remember, in older adults, we saw a difference in the after effect specifically. Here, we see a difference primarily in adaptation, and it's very significant. So this is what we psychologists and we call a dissociation. So we didn't find any differences, any deficits in proprioception. But when we manipulated proprioception in the context of balance, we saw a big difference between the groups. So the difference and the deficit is not peripheral, it's somewhere at the central level of processing. So what is it that people with autism are unable to do? They are unable to reweight proprioception, so to downweight proprioception and to upweight vestibular information when they are adapting during the adaptation phase. And another possibility of these results, of explanation of these results, is that they have problems with the vestibular system. Because if proprioception is inaccurate, then the vestibular system is the only available reliable system that they can use for balance. And if that's broken, then they're unable to do it. So that's one possibility. But the questions emerging, and that's what we're following up with one of my PhD students, is adaptation to inaccurate visual and vestibular environment showing the same effect? So we only looked at proprioception in this. But what happens with vision or vestibular? Is 3 minutes long enough? Maybe if we give them longer, give them 6 or 9 minutes, maybe they will be able to adapt. They just need more time compared with neurotypical controls. We haven't looked at the motor output or muscle activation. Maybe there might be a deficit as well. And is there a way to reduce this deficit? What can they do to reduce this deficit? What can they do to improve their balance? Another interesting issue in autism that is very under-researched is what happens in people with autism when they are over 40 or over 50. Most of the diagnosed cases of autism are younger than 40, because when people over 40 were children, autism diagnosis was very rare. So all these people exist. Autism doesn't go away. But if they are 50 and 60, then and they have balance problems, then they have the effects of aging and the effects of autism on top of them. So that's even more dangerous. So we have to go and look for these people. I don't know how. And how far does the deficit go? This is a 3-minute adaptation problem, but is it a problem of adaptation simply? Is it a problem of motor learning? Do they have an inability to learn? Do they have an inability to do cognitive learning as well, learning in general? It seems that autism is not a learning disability, especially in people who have an IQ over 80. So it's probably like the people we test here. So it's probably not a learning disability, but there's something wrong in their ability to use sensory information. That's it for autism and balance. I'm going to show you a little video now, because I don't want to bore you anymore with me talking. So there's a 5-minute video on our work on Parkinson's disease, where we do work on dance class. We use dance to improve performance in people with Parkinson's. So if you can get the sound, I can show you the video. Can you hear that?
I was a classical ballet dancer. After I retired from dancing professionally, I studied cognitive science at the University of Pennsylvania. And while learning about neurodegenerative movement disorders, I also learned about this program called Dance for PD that trains professional dancers to teach specialized dance classes to people with Parkinson's.
So we started the project a half ago. We were interested in designing a long-term dance program for people with Parkinson's, and we wanted to compare them with other older adults.
I was diagnosed with Parkinson's in September 2009. I had to take early retirement from work. I did admin work and it went the whole right side.
Being able to come out of uni and go straight into a long-term opportunity where it's on a weekly basis and you're getting to know the same people every week and you're able to see them gradually getting better and better at different the techniques that we would do, you'd see people gradually pushing themselves a little bit more into and trying more challenging motifs.
The impact that Parkinson's has had in my life, the loss of mobility, and the need to keep pushing myself to retain the mobility. It's the physical aspects of it which are affecting me far more than the mental ones or the psychological ones. So today was a bit of a revelation because suddenly I started to feel the way I felt back in the autumn, and that the mobility was beginning to reappear and the flexibility was certainly a great deal more pronounced in the last 6 or 7 weeks.
Parkinson's disease, they all have different symptoms, which I was totally unaware of. They each had a different story. They each came to Parkinson's at a different. I actually liked interacting with them, finding out about the person. The Parkinson's didn't define them.
There's a lot of unseen things, the stiffness, the joints, the anxiety, stuff it brings. People don't realise how medicated you can be as normal as possible day. You're always saying how well you're looking, but it's how well you feel inside sometimes isn't showing that either. It can affect your eyesight, it can affect your speech, it can affect your hearing. Anywhere that requires some sort of muscle work can be affected by it. I'm not one for a great deal of exercise, so to have a dance class once a week is good for me.
I would see that people seemed to be walking better sometimes when moving to music, and their stiffness was alleviated after the classes.
It takes me back to my admin work. It made me feel useful again, and it gave me the opportunity to use the skills that I haven't been able to use since I retired. So it kind of gave me a new lease of life being involved in it.
Gentle exercise, music and movement. It's good for the morale. It reminds me of children's parties, various problems that Parkinson's creates in terms of the tendency to get up and make yourself small. Dance helps you to be expansive, throw your arms about and take big steps, and be more aware of what you need to do to combat directly the symptoms, particularly to do with movement.
I noticed when people were concentrating on a particular movement that wasn't involving their hands, that the tremor actually seemed to improve. So if they had to concentrate on their footwork, the hand tremor seemed to get better.
I do notice them becoming better dancers, essentially. I hope that this is also leading to improved mobility in other aspects of their life.
After a series of classes, I would say my balance has definitely improved. I think actually the general outlook just has improved. It gives you a good feeling. I'd be very keen to keep going.
I take other forms of exercise, and obviously the condition is progressive, so one is getting older, so there are other factors at play, and it's hard to tell exactly what the long-term effects of the dance might be on my condition, but it's early days yet.
This project is very different because this project has impact from the beginning. So the local community people with Parkinson's helped us design the project. They knew what the benefit would be for them. The dance classes that are part of our research also have impact in the community because people with Parkinson's are engaging with the classes, and we see that they are happier when they do the classes, they engage socially, and also they improve their motor performance, as we've seen in some of our preliminary findings. So the impact is happening as the research is running, not after the research. So that's it really. We have some results from this study, some preliminary results showing that improves and mood improves, so the rest of some indication that this works in the scientific level and not just at the level of them. To find that there are of we use that didn't work as well. So we're trying to refine the dance classes and to try to redo them better. So we are continuing with these classes, and we are going to also test people with Parkinson's on the sensory integration task that I showed you before, just to see if they have similar deficits with older adults. So thank you very much for your attention, and I'm happy to take any questions you have.
Any questions or comments?
I do. Thanks, Michalis. Great talk and really nice set of experiments, very interesting. I have one question that actually amounted to two. I was thinking about the results you have about the longer time elderly take to get back to baseline, but also at the same time after you presented the Autism Spectrum Disorder results, that they have problems with reweighting.
Mm-hmm.
And if you argue that both have some problems with sensory reweighting in postural control, I was wondering if that is specific to postural control and not just something general to reweighting, like sensory reweighting in double Q experiments that they do in vision research. If this is something specific to posture, or if this is something general to the central nervous system.
So there are studies on visual motor transformations and visual motor adaptation, and there are some deficits there in adaptation, but not very big, not very consistent. There are other, there are bigger effects in temporal order judgment type tasks. So an auditory and a visual cue, and you have to integrate them. They have problems in sensory integration of that kind as well. So there are two answers to your question. One is there is a sensory integration deficits in more than one domain, but I don't think I would call it general, because there are other domains in which it doesn't appear. A more specific answer in terms of balance and in terms of visual motor adaptation is that there is a general idea that people with autism are stuck on proprioception. They use proprioception more than they use vision. So when you when you make proprioception inaccurate, they don't shift to vision or to vestibular. They stay with proprioception, and that's what's causing the lack of reweighting. So it's what I guess what's called a capture effect. So they are, the weight for proprioception is higher for them, and also they have an inability to downweight it. Was that? Did you ask anything else? Okay. Yeah.
Mm-hmm. Back to the experiment that you still didn't run about the manipulating the explicit knowledge about when the platform stopped or not. If you think there is an explicit effect of knowing when the platform stops, what would you think would happen if you gave young, healthy participants a dual task to perform, which would also lead their attention elsewhere, and maybe they wouldn't perceive the motion of the platform stopping? Do you think that would be the same prediction with a different experiment?
This is funny because I've done this years ago for a different reason, and they showed a longer after effect. So you would predict that if they are distracted, they would not notice the platform stopping. But how would that help us with the other question? It's interesting, and it might happen, but how would that help us explain the other effect?
Because I thought you were trying to explain the effect as something attentional or something about the awareness of perceiving the platform.
That's right. Awareness is the thing, yeah.
Mm-hmm. So if you have another task that would divert their attention away from the platform, this would also be evidence that they are actually using some perceptual and conscious information about the platform, not just something, I can say perceptual, but not conscious, but something from the motor system that the system has access to, but that we are not aware of. So if you find some effect of dual task, of longer time to de-adapt, I would say it corroborates your hypothesis that there's some explicit mechanism of perception on the de-adaptation mechanism.
And it's indirect. So are you saying that the fact that it's implicit is better than just telling them? So I'm thinking if they definitely know, you've given them this information, it's clear. I ran a little pilot study about this. Not about the dual task. The dual task is, I've done this study many years ago and I haven't published it, but the study about the explicit information, I'm worried. I've done it within subjects, so I did one condition with the information, one condition without the information. I'm thinking maybe that's not right because people, if they've done it once, if they've adapted once, then they may be better in the other one. So yeah. So I'm thinking, the main thing I'm thinking about is whether I should do it within or between subjects. But in terms of the dual task, it's the implicit element that is I'm a bit unsure about. So they are distracted, so they don't know the platform stopped. So you're saying that. But are you thinking about the perceptual effect or are you thinking about the after effect?
I'm thinking about the perceptual effect affecting the after effect.
So you give them a dual task and you tell them to press the button when the platform stops?
No, in this case you shouldn't because
they were doing too many
you're
things.
trying to divert their attention to the platform. It would be the case for the first experiment when you don't tell anything about the platform. Just to see, because in the experiment you ask for an explicit response from participants. You are turning them aware of the movement of the platform.
Yes, inevitably. Yeah.
Then in the dual task,
actually now I ask them to press when it starts and when it stops, just to be sure that that there is a difference. Sorry to interrupt you.
No. I'm just also thinking about how to test it. It's not an easy question to answer.
And I'm testing it now only in older adults because it's not very interesting with the young adults. Yeah. Thanks.
I have a question, but maybe it's more a curiosity than a question. Because all these experiments are kind of explain why people or old adults fall, right? More often than young people. And one of the reasons is maybe they don't realize that this platform is it's over, right? The movement's over. Do you think this old adults can be trained to improve this kind of motor balance? Because this is why I'm saying it's more a curiosity, because it's not a why, but how you fix it, right? But
I don't know. It's very specific, this. So I don't know. One thing you can do, for example, is you can test it with. You can test it in people with who have done martial arts or something. So people who are physically fit, and see if they've done a lot of balance type training, and see if they would have a smaller after effect. There seems to be, I don't know, some of my students did a little experiment on that, and it seems that people, the older they are, the bigger the illusion is. So over 70 is much bigger than 60 or 65. So that's definitely a main factor. Yeah.
Any other question or comment?
When it comes to the developmental part, to compare the means between
it's okay, I can hear you.
So when it comes to the first part of the talk, that we have the graph between the means of the old adult and young adults. So this was means of groups. But what about individual? Do you think, for example, that this test could be something like a diagnostic tool to see the old adults that they don't have a very good reaction, they have the worst reaction, whether there is also a difference between them and the rest of the group when they were younger? So could it be some kind of diagnostic tool?
Well, I don't know at this stage, but yes, if we can come up with an easier version of it, like that doesn't require, you know, a massive platform and motors and stuff. If you ask someone to stand, for example, on foam, you can probably reproduce that, and that may be one way to assess. Yeah.
I have a question that's kind of related to the question of Ryanis. So you're speaking about the word used is autism spectrum, which might mean that there is different kind of autism, right?
Yes.
So would it be that there is, so you take the mean, but would it be that actually there is a different group and that some are affected in a way that's relevant to this kind of experiment and some are not?
Yes, that is correct. So we are looking at a if you want, a subspace of the spectrum, that is people who are adults, so over 18, and we do that because they don't have any developmental issues, so their balance and their movement control has stopped developing, and they have an IQ over 80, which makes them what we call high functioning. So they don't have any. You must have seen people with autism who show repetitive behaviors and move their head all the time. So these are not that kind of autistic people. These are autistic people that you wouldn't normally say. It's not obvious that they have a problem, that they have like a physiological problem or a psychological problem. They are. You will, if you tell them a joke. And then everyone laughs in the room except them, for example.
Did you control them telling a joke? Or?
So there is a very long diagnostic test that we do to check for the diagnosis and for the severity of autism, just to make sure. And the plan is now in newer studies to correlate the severity with what we find, to see if that has anything to do with the severity of autism or not. So yes, it is a subtype. So the IQ of our autism group matches the IQ of our control group. So our control group is mostly students, so the IQ is between 110 to 115, and autism people are about that. So the mean IQ of the population is 100. And there are some with 130, 140. So there are some people with autism who have a high IQ and they're very intelligent in that sense. But most of them, so if you ask them, most of them don't work. They don't have jobs and they can't work with other people. So they do have serious social issues, but they don't have any intelligence issues and they don't have any obvious movement issues.
Questions or comments?
I want to know why you use Parkinson's disease with depression?
Say again, sorry?
People with Parkinson's disease and depression.
So I've done a study on depression before. That's why I mentioned depression, but that was a different thing. Some people with Parkinson's have depression as well, simply because of the condition. But their depressive symptoms are reduced with the dance classes. It helps them a lot. Is that what you're asking? Yeah.
Very curious about the work. It's really good. I was wondering about the delay effect of the platform. So how long does it take for the platform to sense that the participant have moved the COP?
About 100 milliseconds.
100 milliseconds.
50 to 100 milliseconds. So it's not fast. Mm-hmm. It's not too slow either because you're dealing with a cycle of 0.1 hertz movements. Mm-hmm. So it's not ideal, but it's not real time.
Yeah, I was just wondering if the effect of de-adaptation is a problem of sensory reweighting of proprioceptive and vestibular sensory information, but not just adding something else, that participants, they adapt to the delay, which is something that people usually adapt to. There are many interceptive actions where they manipulate the delay, so participants, they get used to moving their hand, their the projection of their hand as if it was moving 100 or 200 milliseconds later. So maybe the participants, they are adapting to the proprioceptive condition, but also to the delay they are given. And then they might take longer to get back to baseline because it takes longer to de-adapt from the delay and not specifically reweighting proprioceptive and vestibular information. And I have no idea how you would control for this.
It's a limitation of the
Yeah.
of the machine, but the good thing is that this is constant across the groups.
Mm-hmm.
But still you see the group differences. So group differences are over and above the delay.
Mm-hmm.
But I don't know if it would be a way to.
If
No, it's a physical problem.
Yeah. For the platform, you couldn't. But if you use a simple reaching task or pointing task, where you could manipulate visual information and proprioceptive information by covering their hands, then you could test this idea that when you add a delay, they might de-adapt slowly. I don't know, maybe.
Yeah. No, that sounds like something. Yeah, but you have to assume that you're testing the same thing, of course.
Yeah. Which relates to my former question. Thanks.
Thank you very much. Thanks everyone for coming. Oh, maybe there's another question. Sorry, I'm not running away.